Hello, my name is Srikant Guru. Roll number 2153. URN number 210311101. My topic name is SRTF. Scheduling. Multiple processes are simultaneously in the ready state at if and only one CPU is available. A choice has to be made which process to run next. The part of the operating system that makes the choice is called the scheduler, and the algorithm it uses is called the scheduling algorithm. Many of the same issues that apply to process scheduling also apply to thread scheduling, although some are different. Introduction to scheduling. In the old days of batch system, the scheduling algorithm was simple. Just run the next job on the tape. With time sharing systems, the scheduling algorithm became more complex because there were generally multiple users waiting for service. The scheduler must pick the right process to run. The scheduler also has to make efficient use of the CPU because process switching is expensive. Before switching from a process to another process, it is necessary to switch from user mode to kernel mode. Then the state of the current process must be saved, including storing its registers in the process table so they can be reloaded later. Next, a new process must be selected by running the scheduling algorithm. After that, the MMU must be reloaded with the memory map of the new process. Finally, the new process must be started. In addition to all that, the process switching usually makes need to reload the entire memory cache dynamically from the main memory. Doing too many process switches per second can take substantial amount of CPU time. So caution is advised when to schedule. There are a variety of situations in which scheduling is needed. First, when a new process is created, a decision needs to be made whether to run the parent process or the child process. Second, a scheduling decision must be made when a process exists. Third, when a process is blocked on input output on a semaphore or for more some other reason, another process has to be selected to run. Fourth, when an input output interrupts occurs, a scheduling decision may be made. If a hardware clock provides periodic interrupts at 50 Hz, 16 Hz, etc., a scheduling decision can be made at each clock interrupt or at every clock interrupt. Scheduling algorithm can be divided into two categories with respect to how they deal with clock interrupts. A non-preemptive scheduling algorithm picks a process to run and then just lets it run until it blocks or until it voluntarily release the CPU. In effect, no scheduling decisions are made during clock interrupts. In contrast, a preemptive scheduling algorithm picks a process and lets it run for limited time. In primitive scheduling, a clock interrupt occurs at the end of the time interval and scheduler takes control of the CPU. Scheduling algorithm goals. All system families giving each process a fair share of the CPU policy enforcement, seeing that stated policy is carried out balance keeping all parts of the system busy. Best system throughout maximum jobs per hour, turnaround time, minimize time between submission and termination, CPU utilization, keep the CPU busy all the time, interactive system response time, respond to request quickly. Predictability, avoid quality degradation in multiple time, shortest remaining time next. A primitive version of shortest job first is shortest remaining time next. With this algorithm, the scheduler always chooses the process whose remaining runtime is the shortest. Again, here the runtime as to be known in advance. When a new job arrives, its total time is compared to the current process remaining time. If the new job needs less time to finish than the current process, the current process is suspended and the new job started. The algorithm allows new short job to get good service. As an example, consider a system with to users, each of the which has been promised a 50% of the CPU. User 1 has four processes A, B, C, and D, and user 2 has only one process E. If round robin scheduling is used, a possible scheduling sequence that meets all the constraint in is this one. On the other hand, if CPU time is spared for user 1 twice more than user 2, we might get. Thank you.